Here at the Department of Chemical Engineering at ISC Bangalore. And today I'll be making a short presentation on an article that talks shortly about a novel way of purifying water using just carbon dioxide instead of membranes and other traditional methods that we have. The basic phenomenon involved in this process is called as diffusiophoresis. I believe that's how it's pronounced. So this phenomena basically talks about how gradient in concentration can induce movement. So movement of particles. So in this case, we have an analogy. Let's say there's a sugar cube, and it's dissolving into a body of water. So if we imagine a small molecular paper boat that's existing along that current, the sugar molecules, as they move from high concentration to low concentration, they're going to exert some force on that paper boat and it's going to move it along. In this process, however, there's something a little different happening over here. So over here, as carbon dioxide dissolves into water, it splits into hydrogen and bicarbonate ions. Now the thing about hydrogen ions is that they diffuse somewhat faster compared to bicarbonate ions. So as soon as these carbon dioxide molecules split into these two, the hydrogen ions move faster into the water, whereas the bicarbonate ions sort of slack behind. So now what happens is that there's an electric field that is induced because of this, because the hydrogen ions, they're positive. The bicarbonate ones, they carry a negative charge. So now we have these two separated by some space, so there's going to be electric charge in between, and that electric charge is going to push away suspension particles. This effect is pronounced only when we're dealing with very small distances. That is why we need microfluid chambers to carry out this process. Usually they're just 40 micrometers thick, and we'll have one side being exposed to carbon dioxide, the suspension in the middle, and the other side is exposed to air, just so that excess amount of carbon dioxide can just sort of vent out. Otherwise it's going to saturate the particle suspension, and we won't get to see that electric field. The electric field won't be very pronounced, because we're going to have a bunch of H plus and HCO3 minus ions all floating in between. Also, this is just the scaled up version of what we just saw. So each chamber can only cater to small amounts of volumetric flow rates. That is why we need a bunch of these channels stacked around each other to have some to have a setup that can actually purify good amounts of water. The paper presents some very interesting findings. The first point talks about how the number of particles that are found in the filtered stream is almost negligible compared to what's there in the feed. It almost offers a 100% efficiency rate practically. So that's out of 2.2 into 10 to the power 7 particles, we just have 104 in the filtered stream. So that's very good efficiency. The energy required is also very, very less, almost 1,000 times more efficient than ultrafiltration and microfiltration. The process is highly scalable, of course, because all you need is just to keep stacking these channels. And also this thing has a potential to remove biological contaminants, because microbes also carry surface charge, so they will also interact with that and move away in that microfluid channel along with the suspension particles. So these are the references. Thanks a lot.